last meeting, we went over the um, variation of Monte Carlo Tree Search that was introduced in this paper that uses a certain sampling method in combination with the values that the tree learns through simulations to lead to policy improvement. And today, what we're going to do is actually look at a practical example and how this algorithm looks in practice and yeah, like what all the pieces actually look like in code as well. Because, reading through this and looking at how these different um, passes work, it can be a little abstract. So I'm going to introduce, for the purposes of this demonstration, this environment, which is just going to be a version of tic-tac-toe. Now, we can extend games like tic-tac-toe to have larger grid spaces um, and also different win conditions. So instead of like three in a row, for example, we could have four in a row. So for today, we're going to look at this particular variant with an 8x8 grid and a four in a row win condition. And first, I'm just going to introduce the environment and I'm going to show how I'm going to visualize different aspects that we're going to look at later that are related to reinforcement learning so that it's familiar to everyone when we get to the actual like tree search part of it and how this algorithm works and what it's doing. Actually, let me just go to this part of it. So this will be most relevant to what we're looking at today. Okay, so looking at this environment here, I just have I've created like a game, which means I'm just having players take turns until the game is completed. And so that you could see an idea of some like reasonable performance, and also someone asked a question of like what a policy function is here. So normally in reinforcement learning, we train policy functions. Now, in the case of this game environment, I have some like pre-seeded policy functions, which are like computed with some heuristic rules. And I'm going to show what one of those looks like. So what this means is that this game is being played starting from this game state. This just instantiates a game with an 8x8 grid and a four in a row win condition, right? So like this win conditions is like embedded in the game state here. You can see what the game state looks like. It's very simple, right? It's just I make note of where the X pieces and the O pieces are. These are just bit vectors that store their positions. And then in order to check if the game has been won, you have to check if there's four in a row in any of the two of like six different directions. Okay, so what's being shown here is the game board, but also I'm overlaying on the game board the policy function of the two players. So per turn. So like this is the starting turn, and here it's like this is X's turn. Now, this game is being played between what I'm calling like the greedy policy and a random policy. And here, the greedy policy is just a name I've given to this particular strategy in this environment. And the greedy policy works with like this set of rules here. So it's a very simple like heuristic strategy. So if a winning move exists, it takes it. So that also means that it has to check every available move to see if any of them produce a win. Same with if the opponent can win on the next move. So like this is checked first. If this is not the case, if there's no winning move, then it blocks an opponent winning move. And then otherwise, it just favors moves roughly in the center of the board. So that's what's being shown here. Now, like the policy function is a probability distribution over the available actions. And it's just sort of, there's like a heat map here. So things that are this color are sort of like neutral, like close to like, well, this distribution basically runs from like 0 to 1, where 1 is 100% certain action, and then things in the middle are just like in the middle of the distribution. So we can see if I advance this forward, So basically here, there's no move has been played. So now X has played a move here, and then these colors are all the same because, right, this is the random policy. Okay, so the random policy doesn't favor any move over another, and we'll see a random move will be played. Now, every time it's X's turn, we're seeing the greedy policy, which for a while it doesn't really do anything, right, except favor moves towards the center, which is just how it's designed. And eventually, right, so here, right, another random move is made. And then eventually we reach a point where there is a winning move. And then at this point, the random policy, right, all of the other moves are considered 0% probability. And then the winning move is 100%. So it will always play this move from this position, and then that will lead to, right, X winning the game. And basically, like if the random policy plays in this game, it will almost never win because the greedy policy will always take a win when it's available. So is that pretty clear to everyone? Any questions about how the game functions or what the policy overlays are showing? Okay, great. So now so this is like a game where the players alternate. Now, to avoid some additional complications, I'm going to discuss this algorithm, this whole tree search algorithm in the context of MDPs, or like Markov decision processes, which are things in reinforcement learning where a single agent is acting in an environment. And this tree search and the policy improvement works in that context. It also works in the self-play context where there's two different agents competing against each other. But for now, like the essence of the algorithm, really, it's easier to understand if you think about it in the MDP environment. Now, this game I've created here is not an MDP because there's two different agents, but we can turn it into an MDP by fixing one of the opponents. So I showed what the greedy opponent looks like. So what this is going to do is it's going to construct an MDP with this greedy opponent. So the O player now, in this case, will always play with the greedy policy. And then whoever we are like interacting with the MDP, we are then going to make turns as the X player. And then there'll be a state transition, and the transition will involve, the O player, the O opponent making a move, and then we'll see the updated state after our opponent has produced a move. Okay, so now this is an environment with a single agent that can take actions. And this transition function for this environment is also, it's somewhat stochastic because we know that the greedy player, like sometimes the move it selects is deterministic, like in this situation, but there's other times like earlier in the game where the greedy player has this distribution over actions. So now we can measure the performance of like if our agent now has random performance. This is like how well does the random player do in this environment? Like this is not a trivial environment because we are playing against the greedy opponent. And we can see that the average performance for the random player is this value of like, if it was -1, it would be a loss every time because I also have to make this MDP environment, I have to assign a reward value to every transition. So because, this is a game with sparse rewards. So there's no reward experienced until like the final move, whether it's a win, loss, or draw. And because now this MDP is from the perspective of the X player, the rewards will be 1 for X winning, be 0 for a draw, and -1 for X losing. So here, if we just measure this random performance, it's close to -1. To convert this to a win rate, we just have to add 1 and divide by 2, right? Because we have to, rescale -101 to between 0 and 1. But this will be equivalent to the win rate, and we could see that, even against this greedy opponent that's not that sophisticated, but, we're winning less than 1% of the time. with this. And now we can generate an episode in the MDP as opposed to what I showed earlier was these players now alternating turns. Now that this is an MDP, if I show an episode, the way it works is here I've this orange is the action that the agent took. This is like prior to the update. So basically from the blank board, our agent now is going to make this move. And then when we go to the next step, we have, as part of the transition, now the greedy player has responded. But for now, from the perspective of the agent, we're only making moves, X moves in this case. So every time we make a move, the environment provides the transition, where the O player then responds. And then this is going to end in a loss, of course, because we're playing randomly. So here, the O player has succeeded on this diagonal. And these are the rewards. So for every step, right, it ends that there's no reward until we get to the very end. And on step 12, there's a reward of -1. And this is what all these MDP episodes have, this structure where we have the list of all the states visited, the list of all the actions taken by the agent, and then the rewards. And then this is the terminal state. Okay. Yeah. Any questions about this so far? Okay. So now I'm going to show, we're just going to do one round of what we would traditionally do in reinforcement learning, which is, select one of the many algorithms that we have available to us. Here, I'm going to use a policy gradient method, and I'm going to train an agent to succeed in this environment. And by succeeding, by maximizing reward, that because of how I've structured the rewards, that's going to be equivalent to maximizing the win rate. And I have a way to set this up. If you're interested in where all these things come from, all this stuff was developed in the series you can find in like the reinforcement learning playlist, where we looked at the Sutton and Bartow textbook. But all these algorithms, like here, this setup function creates some different training functions that you can choose from. But here, I'm just going to use the this Actor-Critic policy gradient method with nonlinear approximation. So also, in order to use one of these methods and to use any like AlphaZero style method, we also need to create a feature vector that our function approximation is going to use. So here, the feature vector construction is really easy. Here's an example of what it looks like. I'm forming it into a matrix here, an 8x8 matrix, but really like the vector is all these columns of the matrix are stacked together to be a length 64 vector. And I'm just assigning the value to every position on the board. So empty squares are 0, 0 squares have a value of -1, and then the x squares have a value of 1. Okay, so yeah, the feature vector is very trivial. And then this is doing, so now I'm going to train an agent. And with the Actor-Critic algorithm, it's training a policy function and a value function simultaneously. They share an architecture here where they both have, this just means that they have 2 hidden layers of size 64. It's a dense network. As well, it's just a fully connected neural network. These are learning rates, and this just means it's being trained over 100,000 steps per round. Now, this training function also trains over multiple rounds and tracks the performance over each round. So here you can see, like, initially the baseline reward is this value close to -1, and then as training proceeds, it slowly improves. It actually has sort of a very rapid improvement after some very, very minor improvements. And then it ends up stopping at this point, this level of success with the reward. So the best it could possibly do is an average reward of 1, which would mean it would win every single game. And in this case, just because I've limited the number of steps here, but this sort of stopped improving, at least like the way this training loop is designed. It stopped improving at this level of performance. And we can see, yeah, the result of this is, yeah, so we have the parameters, the final performance, and then, yeah, these are just like statistics gathered during the training process. So now we can measure the performance of this. We see in the training loop already like what it experienced during training. Here we can verify that by doing, this is gonna just average the performance of a bunch of episodes in this environment using this function. So at the end of training, right, we have a policy function, a value function. The policy function does produce a whole distribution over actions, like is shown here. But really, like to test it, we just need a version of that that generates a sample from that distribution. So that's what this means, this function here. And then we get this performance around 0.6, which matches what we saw in training. Now, converting that to win rate, it's about an 80% win rate. So yeah, like the performance is certainly much better than the random policy, but still not perfect. And we can see now what the distribution looks like of this function as opposed. So this is something that's been trained as opposed to the heuristic policy function we had for the greedy policy. So here is an example of the policy winning. We can see it wins in a very short number of steps, but you can see it favors these positions in the middle of the board. So what's being shown here is I'm overlaying the policy, and then again, like the move it's actually going to select from this state, and then yeah, the O, response move from the greedy policy. We can see here so the Actor-Critic method also it does produce a value function as well as the policy function. Now, the policy function is what we actually need, like that's what's used to select actions. The value function is only used during the training process to reduce variance and to allow us to update the network before the episode is terminated. So it allows like a degree of bootstrapping in the training. Otherwise, we'd have to wait until every episode terminated before we had any data we could use to update the policy function. But we could see, because I've cut off the training pretty early, even though like the policy function clearly performs well, the value function is not that informative. Like here, there's this value, which is sort of, you could see that as I advance this forward, the value estimate isn't changing. And as we get closer to a win, like here, we're much closer to a win than before, the value should be increasing, and it's not. And that just means the value function has not converged to anything useful because, Actor-Critic methods don't, they're much more likely to have like the policy function converge than the value function converge to accurate values. Like they could be relatively accurate, but on an absolute scale, they, unless we train for much longer, we shouldn't expect them to really match like the true value function. We can see here that in the situation where the policy we've trained wins, it just favors these moves in the center, and if it gets lucky where the response never blocks it, it just forms this stack of 3 moves in the center, and then like once it has this situation, right, where it has 3 in a row, now it has a double threat that can't be blocked, and then it just wins on the next move. So pretty straightforward when it wins the episode. Now, of course, like we know this is a flawed policy. It doesn't win 100% of the time. So similarly, we can look at an episode where it loses, so this, like the winning episodes happen to all be very quick. So, right, this completes in only like 4 steps. It basically just makes a stack of squares and then it's over. The loss episodes, what they have in common for this policy is they're all much longer. And what happens is that the initial attempt to win in the center of the board fails, and this time, right, it fails because the opponent has placed a move towards the center, which prevents it from getting this 4 in a row as easily. And now after this move, or sorry, this one. So after this final block here, right? Now we're in a part of the state space where the policy function has not learned what to do very well. We can see now we have now like the distribution is much more spread out. It ends up, we could end up randomly sampling from any of these moves. It ends up picking this one. We can see that for the remainder of this episode, the policy function really has very little idea of what to do. Like it never actually gets updated to a state where it has a clear distribution that favors one state over another. I mean, we can see like minor things changing in the policy function, but it's clear that it's just not trained long enough to learn anything useful about this state. Yeah, and we'll see this like if we generate episodes, about, as we saw, about 20% of the time it will lose, and it will lose in this type of scenario where its initial attempt to win fails, and then it's a bit lost in the state space. Okay, so that's sort of the end of the introduction of this environment and what a traditional RL method looks like. So next, I'm going to move on to the tree search part of this. But if there's any questions so far or clarifying things, I can answer that now, because everything we do from here is gonna it's gonna build upon this stuff so far. Okay, so I will move on to now the tree search part of this. So to introduce this, the reason why I trained this policy function that is an imperfect policy function is because it's what we're going to look at in the first use case of this tree search. And that is to do something in real time to improve a function that we already have. So that function, I showed you, it has like an 80% win rate. So the idea is like maybe when we're interacting with the environment, we actually have like a time budget to work with or a computational budget. So if we look at the policy function we had, we can evaluate it very quickly, a matter of like microseconds. So if we're given like a few seconds to work with in a given environment or, playing a game, then what should we do with the policy function in order to get the most out of it? And that's one of the motivations for what's in this paper and any sort of tree search method, but it's a real-time planning algorithm. But all these different algorithms, they're trying to figure out, what is the best way to allocate computational resources in real time to get the best outcome. And in this case, the best outcome would be an improvement upon the policy. I mean, this algorithm we're going to look at guarantees in expectation an improvement upon the policy. Now, it doesn't mean it's the best possible thing that we could do, but it is one of, the only examples of tree search that does guarantee this improvement, whereas something like the original version of AlphaZero does not. There are situations where it can actually have a worse performance than the underlying policy used for the search. So again, we went over more of the mathematical details of this in the last meeting, which you can find. There's a recording of it. But now we're going to look at more like what is actually happening with the algorithm in real time and how does it lead to this improvement. And I'm going to by like discussing this algorithm, it has like different names. It doesn't have a great like flashy name like AlphaZero exactly, but I'm going to call it this Gumbel Top-K algorithm. It's because a Gumbel is the sampling method being used. So it's a form of random noise that's being used to sample from distributions. And this algorithm is going to repeatedly sample from different distributions, policy distributions, just like the one being shown here. And the baseline distribution it's going to sample from is actually the starting policy function that it's given, right? So like the one that we're trying to improve upon. So in the case of this example, like we've already trained this particular policy function. This is its output, or this heat map represents its output in this particular game state. And this is one of the things that the tree search is going to use. So yeah, but the two key points for this scenario that we're talking about is we want to improve upon an existing policy function that we have using some kind of simulation budget, either computational budget or a time budget. And then we also want something that can succeed even when the number of simulations is very small, and in particular smaller than the number of environment actions. You see, in this environment, we have 64 actions from the starting state. That's the size of the board. But we'd like something where even if we just have a handful of simulations to work with, we still get some sort of improvement. And this is a regime when we have a limited number of simulations that traditional Monte Carlo tree search can't operate in. Because in traditional Monte Carlo tree search, you don't get any useful information until you've sampled all of the available actions at least one time. And also, traditional MCTS doesn't have a straightforward way of using a policy function. So that's that it's improving upon. So to use this algorithm, there's a few like requirements and hyperparameters we need to think about. So one of them is this top K value. Like I mentioned, I'm going to refer to this as like Gumbel Top-K. In this case, top K refers to a decision about the maximum number of actions that are going to be considered from the search state. So like if you look at it, if we're starting out here and we were to apply the search algorithm, instead of considering all of the actions, I mean, we could set the top K to 64 in this case. That would consider all of the actions. But oftentimes, because our simulation is limited and there's also environments where we want to use this, where the action space is like many hundreds or even thousands, then we want to limit the search space, the action search space, from the root. And in this case, like when I refer to the root node, I mean that is the part of the search tree with the state that we're considering to make a decision in. So like we're giving the search, this is the state we care about. The search function may go through and visit other states, but the root is the starting point. It's the state that we actually need to make a final decision in. So we have to provide the algorithm this value that we're limiting. Now, in the paper and in a lot of applications of this, usually use powers of 2 because of what we'll see later, how this algorithm works. So they use a value of 16, but you could use other values like, but probably it's good to stick with powers of 2. And it should make some sort of sense with your simulation budget as well. So like NSIMS is another hyperparameter, is the number of total simulations that we're allowed. And every time we run a simulation, it means we simulate transitions in the environment and we observe what happens. These are like hypothetical transitions. So what I showed here with this episode is actually like different states that are visited in an episode. What the search will do is it will generate its own hypothetical, not full episodes, but transitions in the environment, and then collect information about that. Now, if the total number of simulations is like 5, for example, but the top K value is 16, what's going to happen is this will artificially be limited to the number of simulations. So this also works in the regime where the number of simulations is less than the top K value. It's just that then we only consider, like 5 actions if we only have 5 simulations. And that would be like a limiting case of this search that actually reduces it to a far simpler algorithm, because the tree search ends up having these different stages as it goes through the tree. But if we're in that really limited regime, then it's a lot easier to understand what the algorithm is doing. It's quite simple, but even that reduction of the algorithm still leads to a policy improvement, which is why it works. Whereas normal MCTS, if you tried to run it with only 2 simulations, it wouldn't do anything. It would have, strictly worse performance than the underlying policy function. Then there are a couple of constants that are used. These are used later to calculate the improved policy. They're basically constants that control the importance of the data that was collected during the search and balance that with the policy distribution that we've given to the search, right? So the whole play is like, we're trying to improve upon an existing policy function. That's what we provide the search. And these values, at least in the paper, they recommend that this value be like 50 and this is 1. And they said that those hyperparameters actually worked across a lot of different use cases and they didn't have to be, tailored, which is nice. And then again, of course, we have to also provide it with a policy function. Now, in the case of the tree search, this is a function that's going to provide a value estimate and also logits. And these logits are, you can calculate them by just taking the log of the policy function, but they're also the things that you can exponentiate them to get back to the probability distribution. So what I'm showing here is like this heat map is like 0 to 1 values. This is like the actual distribution, whereas the logits would be if I take the log of this, so then they would basically all end up being these large negative values, because the highest value in the distribution is 1. The log of that is 0. The logits will be from 0 to like negative infinity in the case of actions with 0 probability. But the reason why we need, the way this algorithm works, and you can show it here, keeps referring to these logits. The reason why you produce logits is because this Gumbel sampling method, the way it works is if you have a distribution and then you convert it to logits by taking the log, then if you add this Gumbel noise, this is just a particular random variable. I showed it last time on the Wikipedia article on it, but there's a certain way to generate these. And then this, if you have then a new vector, well, you can call these like scores, but it's the logits plus this noise value. And then you can, if you rank, if you then select either the highest value or the top 5 values, it's a way of sampling from this underlying distribution. So anytime you see this plus this GA, this Gumbel noise, that is a version of sampling from a distribution. So in this algorithm, after the search takes place and we have these Q values are then values collected inside of the search tree from the simulations, this argmax here at the end is effectively sampling from this new distribution. So now this is not a logit value. I mean, this sigma is sort of hinting at like, we're sort of treating this as a logit. The nice thing about logits is they have like this unbounded range. So we don't have to worry about some of the problems that AlphaZero has, where it's like combining a probability distribution with Q values. Here, we have these Q values we've learned, and then we use them and combine them with the prior logits to have this new policy. This is like the policy from the tree. And the nice thing about this algorithm is at the end, it does actually sample from this distribution. And this is also the distribution that we believe is an improvement. So we have both at the end of the search, the action selection, that the search thinks is the best candidate action. And also this whole distribution that, like, it's not guaranteed we get any one of these values, right? Because we have this Gumbel noise in here. So even though it looks like this is a deterministic selection at the end of this, the thing that makes it a sample is that we have these noise values that we keep propagating through. So what I'm going to show now is like what type of data the search actually collects and how it makes sense using this testing environment. But first we have to I'm making this test function, and this is just the policy function that I'm going to pass into the search. And I'm just going to use, this is the Actor-Critic solution that we saw earlier, we computed. So it produces the policy distribution and the value estimate. Also, this, just for efficiency, this function actually, the way it works is it updates a vector with the logit values. So here, like, what we need in order to run the algorithm, we need these logits, right, from the policy network. But here, instead of like generating them one at a time, this function just populates this vector with them here. And yeah, it converts them into logits here. And then it also returns the state value estimate. So, yeah, so I already mentioned the number of simulations that hyperparameter is used by the search. And we're trying to select a final action, which is an improvement over what this policy function would normally do. So first, we can look at what the algorithm actually does when the number of simulations is very small, because this is easier to understand what happens after. So here I have this slider bar to control how many simulations I'm considering. I'm setting K to 16. So this is like the max I would consider. But here I'm looking in this regime where the number of simulations now is low. So this is the search function now being run, and it's getting, right, the actual like environment is passed to it. This is just the discount rate, because this is a game. I'm not worried about discounting here. I just care about the final outcome, not how long it takes to get there. The discount rate is 1. This is then the policy function being used. This is one. Actually, I forgot what this parameter is, but this is so I'm running the search from the initial state, so just the blank game board. And then the number of simulations is just given by this slider bar here. The depth here, this is a way to like prematurely cut off the search if it gets too deep in the tree here. I don't actually want it to ever cut off, but these games, right, especially this particular environment, a game will never be longer than like 32 actions, right? Because there's the X move and then the response move. There's only 64 total squares. So if I set the depth to 1,000, it should basically never prematurely cut off. So once the search is completed, it returns these 5 things, which are shown here. The first thing is just the action that it actually is recommending. Then these are all the components of the tree. So there's the visit counts, the action values. These are like estimates for every state, and these are all structured in dictionaries. So it's a mapping from the game state to these various things. And each of these things, like the visit counts and the action values, are every state then has a vector of a 64 length vector, because those are all of the possible actions. The ones that are invalid are masked out of that, so they will never be visited, because you can't take an action in a square that's already occupied. So it, like the visit counts store how many times that action has been tested from that state. And then the Q value is just the tree value for that state. So once it tests an action, it collects data about the transition, and then it uses that to update the action value. That part is the same as what occurs in normal Monte Carlo tree search. So we have these dictionaries here. So what I'm showing here, this is showing like all of the elements that are saved in the tree, all of the keys, so all the states. We can see there's only 6 states in the tree. And if you can look at each of them just correspond, well, there's like the one state, right, which is from the initial board. And then all these other states are just game states where we've made a single move, right? Because there's only 6 simulations here. So all the algorithm has been able to do is test 6 different actions. And every action it tests, it basically gets a new board back. So this is like the board that was received after this action was taken. So it just has a single example of the next board from every action taken. And that's all the time that the simulation had to do. After that, the simulation is over, and all it can do, what we can see actually an example of what, this is the visit state. So this is the value estimate cache. So what this is every time it sees one of these new states, like this is after this action was taken, it produced this state, then it expands a new state. And for every visited state, it initially calculates the state value using this function, using the state value estimate. So the reason why we need the state value estimate, just like we actually need it for doing Actor-Critic training, is in these early parts of the search, we don't have any further information. We have to then evaluate the state we ended up in and make a judgment about that. And here that information is coming from the value function, which, as I said earlier, it's not a very good value function, right? The values are not that distinct between states, but nevertheless, this algorithm should still be able to produce an improvement even with a poor value function like this. Now, if we actually look at one of these states that we're in, like here, I'm taking the action values, and there's no information in this state. Like here, this should be the visit count. We can see that none of the actions have been visited, right? Because we only have 6 simulations. So all that the algorithm could do is visit one of these states, calculate the value estimate, and then propagate that back up. So it didn't have time to actually visit any of the actions in this state. And that's because of how limited the number of simulations is. So now, where did these 6 actions come from? And actually, I'll show it here. What does this actually look like? So here now I'm showing the root of the tree. So what I'm overlaying on top of this is the policy function that we're working with. So this is the policy function from before that we trained with an Actor-Critic method. This is what I'm actually providing to the tree. This is the move in orange that it's selected. And then these numbers here are which actions have actually been visited as part of the search. We can see that there are 6, 1, 2, 3, 4, 5, 6 actions have been visited. And then these are the action values that have been updated in the tree. But again, like these action values, they are the only information they have is just evaluating the value function one time at one of the transition states that it ended up in, right? And we know that the O response is stochastic. So this value estimate is very limited. Like to get a better estimate, we'd have to sample way more of these actions to see more O positions and then get, and then we'd end up averaging together a bunch of these value estimates. But for now, right, all these other action values here are, I mean, they're being shown 0 here. Really, they're not just 0. They're also marked as being unvisited. So the values aren't really 0. They're actually more like empty values. But that's okay, because from the root node, we're only going to consider the actions that we actually visited for this, which is why here you can see it basically visited all these actions, and then the one it selected happens to be the one in the middle here, which I guess probably has the highest action value. I mean, we can see it listed here. It does, in fact, have the highest action value. So there's some consistency between the policy function and the value function, right? That like the policy function favors these actions, and then it turns out also if you select this action, the value estimate is higher than the other options. Now, so the search algorithm selected these 6 actions to simulate, which it could visit one time. And if you look back at the paper, the actions that are originally selected are selected from this arg. Here they have M, I'm calling it K, but it's the top K, or here like the top 6 from this. And because this is this Gumbel noise value, so what this is doing is it's just sampling 6 actions from the policy distribution. That's it. So when this algorithm is running with only 6 simulations, the only thing the algorithm's doing is it's looking at this policy distribution. It's selecting, 6 or whatever, however many we tell it can, of these actions to look at. And then from these 6, it evaluates the value function at the transition. So it's kind of like doing a 1-step look ahead and then bootstrapping that value. And then it's selecting the best action value it got from that. Actually, it's not. What it's doing then at the very end of this is actually combining the logits with the action values here. But I'll get to that a little later, what the actual improved policy looks like. But it's not quite as simple as just whatever has the highest action value wins, because it also still puts some weight on the original distribution. So is that any questions about what's being shown here, what states the algorithm is visiting? Or what, the information contained in the search tree. I'm trying to show sort of at every step of the process what information's actually been collected.
I think, the current, system, makes sense, given that the previous one was, the sampling collections, and then the ones are just the states that were previously visited, and then the ones just the probability of action of picking a state out of the Monte Carlo Tree Search possible states.
So yes, this is being recorded, and if you look at the meeting description, there's a YouTube playlist for the previous meeting. So in the last meeting that we went over more this algorithm and how it actually does lead to a policy improvement. What's even in this extreme regime where all we do is sample a few actions and evaluate the value function once, this selection process at the end, because it's using, one of the tricks of why it works is because it's using the same noise value here as it does here. And then this combination and the fact that this is an argmax and that this could be any monotonic function of the Q values. Here it's using these C constants that normally this value is 50. And then this, in our case, would be 1, right? Because the most any action's been visited is 1 time. But what this does is just put more importance on the Q values the more samples we collect. But, this could also just be the Q values on their own. So basically just combining the logits and the Q values with this, basically if two logits are of equal value, then this will tend to favor a higher Q value, all else being equal, but there's also the noise to worry about. So this ensures that we're always, see, like the problem with the other version of MCTS, what happens in like AlphaZero, is there is a lot of deterministic action selection by ranking things, ranking scores. And there's some perturbation with noise, but the perturbation with noise is actually to make the behavior more random. Here, the noise perturbation does make the behavior random, but it only makes it random in the sense that we're sampling from these distributions, both the original one and the updated one, rather than just doing something deterministic plus some random noise, like we would do in reinforcement learning value training often, is we would follow like an epsilon greedy policy, where to make sure we keep exploring, some percentage of the time we just take random actions. And that works in reinforcement learning. But in this case, where we're trying to have a policy improvement and doing this search, we don't just want to perturb with random noise. We want to use the random noise in a particular way. And the way it's being used here is to consistently sample from an improved distribution. So now, so far I showed, if you're in this really limited regime, the initial sampling here, it's just sample 6 actions from the starting distribution, which here, it's not too surprising that it picked the 3 actions that are non-zero probabilities. It also happens to pick some other actions because it's sampling without replacement. So it makes sure that every action is a unique action. Now we can look at it in a more typical regime where we have a lot of simulations available. So here I'm going to say, what if our simulation count now greatly exceeds the number of sampling states, the K value, 16. And here, what the algorithm does is it distributes the simulations in stages, and it follows this process known as sequential halving. And the goal of this is to cut down the number of actions it's considering until there's just one left, but to also make sure that there's a simulation budget that is spread out between all the stages. So we have a risk of prematurely cutting away actions that could be good, but we're always keeping the top half of the actions we think are the most promising, and then we're allocating more simulations to those actions to better distinguish them. So we can see here, I'm running the same search now from the starting state, but with 200 simulations instead of just 6. And I've also turned on this messaging, so it's going to be a little verbose about what it's doing. So here it's saying, so it first selects 16 candidate actions, right? These are the candidates. And these 16 are, again, sampled from the starting distribution here. Okay, 16 unique actions sampled. Then it allocates over 4 phases. Now, the reason there's 4 phases is because it cuts the actions in half every time. So first there's 16, then 8, then 4, then 2. And on the stage where there's 2, all the remaining simulations are allocated to the 2 remaining actions. And then from there, the best of those 2 is selected. But the reason why it's done this way is the idea that as you get more refined in which actions you think are the best, you want to then allocate more resources to the more promising actions. And there's a balance. Like you could try to do that at the very beginning. Here, this sequential halving is just a way to do it in stages. And it's been shown in other types of problems, like in bandit problems, that this is a way to minimize simple regret, which is basically at the end of this process, we don't want to feel as though there was an action that we should have spent more time exploring. Like we want to make sure that at the end of these 200 simulations, we have done our best to gather the information to figure out which is the best one. We don't care about if while we were doing the simulations, we selected the action. Like in normal MCTS and in like AlphaZero, the selection goes more like during the search process, the algorithm is trying to select the action that it thinks is the best. And it's always doing that. This is not actually doing that. It's more trying to distribute the simulation so that at the end of the 200, it knows the best action, right? It doesn't need to make sure that every step of the way it had the best, because we know the budget ahead of time. Like we know what we have to work with. And all we really care about is the final recommendation. We don't care about, the intermediate recommendations. Also because at the end of the day, we're going to have this updated distribution, which uses all the information we gathered. Whereas with AlphaZero style algorithms, they actually like use the visit count, usually like not just the Q values, but the actual visits themselves. So like what's being shown here, or what I'll show here, these numbers illustrate the number of visits to each action. And in normal MCTS, we would visit these actions with a different way of using the tree statistics. And then we might look at the visit distribution and say, well, we think the updated policy should reflect the visit distribution. Here, we're not constrained by that. We're not actually using the individual visit counts to make this final policy recommendation. We're using the Q values and the logits. So I showed now this. We have 200 simulations. The way the halving works, it tries to allocate the simulations equally between all the phases. The effect of that is that as we get further into the process, there's more simulations assigned to each action. So right here we have 16 actions, 48 simulations, which allocates 3 simulations to each action. So at every phase, the simulations are evenly distributed between the remaining actions. So in phase 2, there are 6 simulations per action, per 8 action, 48. So there's 48. And then if there's any rounding error, it ends up adding extra simulations to the final phase, because we think that at the end, these are the 2 best options. So it's better to explore those actions more deeply in the search tree. And at the end of this, we're left with 0 budget, and it's done. So we can see here now part of the search, now this tree actually has 200 states in it. And we can see now there's been more exploration further into the tree. So we have now examples of moves here where now 2 moves or 3 moves are taken. Yeah, this is just a function of having a bigger simulation budget. And also, if we look at like, this is just, I've just taken one of the, this is like looking at the non-zero indices of the visit count of something deeper in the tree. And this just means that this, whatever state this corresponds, it's actually this state here, that this state, once we got to this state in the tree, it also visited action 44. In this case, it was 1 time in the tree. But depending on what state we select, we can see there were visits in those non-root states. Here, I'm just showing the root state, and you can see how the simulations were distributed now. So now we have, there's only 2 actions that have the most simulations. That's consistent with the halving procedure. So at the end, initially, there were just 3 simulations to each one. So we can see all of these things marked 3. These are actions that were cut out in the first round, right? And then there's ones with 9. And as you get to the smaller and smaller action counts, you get higher values. So at the end of this process, the best action was selected from these 2 actions that were left after the halving procedure that each have 49 visits each. We can see this matches what is described here in the paper, where this is, again, that I chose the same parameters here, but it's 200 simulations, 16 actions. So it initially assigns 3, then 6, then 12, then 28. And this 28 plus 21 is the 49 that you see here. And yeah, here, right, 28 assigned at the very last step to each of the 2 actions. So that's the difference in how things are allocated If we're in this limited regime, we just spread the simulations across however many actions we have available. Here, this is as we get more information from the tree, we allocate more and more simulations to the actions that we think are going to end up being the best in the improved policy here, which is actually, so instead of just sampling from the distribution that we started with, after every round, we also now have information from the Q values. And that information is then used to update how we're sampling. And, refocus the samples based on the action value information that we've received. Okay, so that's how the halving procedure works. Any questions about this? How the simulations are allocated? I'm also showing here that the action values now, which has 16 action values, and the ones in the middle here have a lot more samples that they were collected from. So the next step is to discuss how the information now in the search tree is used for policy improvement. And here I already showed it in the paper, but just to reiterate, we have the prior policy logits. We have, right, this is like we get from taking the log of the starting policy. Then we have the improved logits, which we get from adding to the prior this function of the Q values that have been collected. And there's this, some of these other parameters doesn't really matter. This is just a monotonic function. It could be any, it could just be the identity function as well. This is like the number of visits. So as more states are visited, there's more bias towards the Q values. So after each round of the halving, we use this improved policy to sample from. And actually, if we go further into the tree, then once we simulate a node and we have an action, if we then revisit that in a new simulation, then we have the opportunity to then also test out an action in one of the deeper nodes. And when that occurs, we also use this improved policy. But in that case, we're considering all the available actions, and a lot of them don't have Q values. So in that case, we just fill in the Q values with the value estimate, like that we're providing the function, which means that they're all going to share the same value originally. So when we first visit a state, just like when we start the sequential halving here, we are just sampling from the prior distribution. It's only after we start accumulating some visits that we have now a difference between some of the Q values. But the sampling works where it tries to match then this improved distribution at all of the subnodes in the tree. So now we can do something where we'll actually be able to verify that this whole search process leads to an improvement. And first, we have to do something here. This is a function that basically takes parameters of the search that I want to use, and it produces a function that allows me to generate an episode now, not just using the original policy, but using the search policy. So this is what I'm going to call one of these, this Gumbel MCTS episode. So this is an episode generated in the environment. Now applying the search function to this the policy distribution test, which is the same function I got from doing the Actor-Critic training. So here it looks a lot like what we get when we just run an episode. We have the states that were visited, the actions taken, the rewards. We can see here this is actually a game that was won by the policy. And then this is important for later where we're trying to accumulate data, because this function that accumulates an episode, it doesn't just accumulate the normal episode statistics. It also saves information about the search tree. So here, this episode, right, was 7 steps long. And we could see here, there's now this thing called MCTS data. And this is data from the MCTS search. So here, like, we have the action selection, right? So we have the final action that the search took. But we also have this information that we're going to use later on. And now what I can do is actually show this episode and how the search policy compares to the original policy. What I'm showing here, I'm showing the visit counts on both, but this board is showing the policy function that we started with. And that's the one right from the Actor-Critic training. What I'm showing here on the right is the improved policy. And that's what's being computed here. So this improved policy is actually using all of the search information. So once we've, conducted one of these searches, we have all of the statistics from the root node, even from the states that were only visited 3 times. And we can use all that combination of information to compute this improved policy. And then these are the action values from the tree as well, the sort of completed action values. So we can see there are some values here that all share the same value. These are ones that were filled in with the state value function, okay, for unvisited states. All the other values that are distinct, like these values, are ones that actually have a non-zero visit count. But yeah, in this case, the improved policy can actually also consider the unvisited states as well, not just not just the visited states. So we could show how this episode works. So we could see from as a starting point, right? The search concentrated its final action selection in 2 of what were the only 2 of the 3 candidate actions from the original policy function. And as we so just to verify this is working correctly, we want to make sure that there are situations where if the policy function has a clear action, which it favors, which is actually better, that the search also mimics that. And here we see that even though it did sample all these other actions, it ended up concentrating most of its samples on this one. And now its behavior is the same as the policy function. So again, like this episode is not proceeding where so far the 2 functions have similar behavior. But we could see that this is one of those example episodes where it can't win. It doesn't win on its initial attempt. So, right, it's going to make this move here, which is also what the original policy function would have done. And now we're in the situation where this policy function usually loses, which is it's in a game state where it doesn't have a clear answer for what move it should make. Now we can compare that to the search function. Now, actually, what is a little bit of a subtlety here is we could see here, so this orange X is the action that the search actually took. And this X is always going to be in one of the 2 most sampled actions. Here this search is actually running with 1,000, a simulation budget of 1,000. Okay. So because of the sequential halving, the only actions it's going to choose from at the end of the search are one of the 2 with the most visits, right? Now, if you look at the improved policy distribution, right? So what is being overlaid here is the improved distribution calculated from the tree. And we can see that the action it actually took is not one of the actions with high probability. The actions with high probability are actually these 5 actions that only had 15 visits each. And the reason why this happened is because once we've completed the search, right, at the time when all of the actions had 15 visits, these were eliminated, which is why they didn't accumulate more simulations. However, when the search proceeded longer, it turns out that the actions it evaluated after that and collected data on, in retrospect, they actually end up looking worse than these actions. So if we were to look at this tree in retrospect, and what we'll do later with this algorithm is use it to train a policy function, then we would say, well, in retrospect, we actually want a policy function that selects these actions more often than this one. But this is what was actually selected during the search, right? Because we don't have the benefit of hindsight. Like the way the sequential halving works is we're sort of stuck where if we prematurely eliminated a good action, that's just the way it is. Now, luckily, that might be bad for a single action selection. It's not a problem in the long run because we're still sampling from this improved distribution. But this is the action selected with the best information at the time that was available. And this is the distribution calculated retrospectively with the whole search tree. So now, but we could see now that it is favoring, a particular action selection, which is probably different. I mean, it's possible that our original function would do this. We can see that even on the next step, so this function had selected something that in hindsight is not as favored maybe as these actions. But now that it saw the response, so where was the response move? So the response move was here. Now that the response move is here, now the search has a clear action selection. And if you're looking at this game state, you can see why this is a better action selection, right? Because this creates a double threat. Once this move is made, there's no way for O to stop us because it can't block both sides simultaneously. So this is a situation where the search, even though the policy function, it doesn't have embedded in it the information about this state because it wasn't trained enough on a state that looked like this. But the search function is able to see, okay, like this action selection is in fact better than any of the others. We can see it reflected in the action values here, where all these action values are bad or close to 0.5, and this action value is much higher. It should actually be 1 but that's because of the limitations of the value function not being accurate. We know looking at this that once you've made this move, you have a guaranteed win. So now, and then, like the winning move is made then after that. And in fact, it does show. I don't even know if the winning move state has a value of 1 here, but I believe that there might be another winning move or something that leads to a winning situation in this as well, but it did select this move. So this is it's just one example. We can see that this is one of those game situations that the policy previously lost, and the search is allowing it to win. And it's using the policy function for something, right? It's using it to concentrate. Like here, this move was one of the moves considered by the policy function, right? It's not like this move. The reason why this was never sampled is this is a very low probability move according to the value function. So is this one not sampled? Now, if the policy function's really terrible, its distribution won't even have information as good as this, where like it won't even be good at directing it. But like the point is, no matter how bad the policy function is, this can at worst lead to the same type of performance, and in expectation should lead to an improved performance. So this is like a single episode, right, where we see some evidence that it's doing better. But we can also evaluate this these statistics. So this is the performance of the original policy function that we were looking at. You can see it's about 0.6. This is not the win rate, right? This is the average reward, which we would have to scale it up to the win rate. So this 0.6 corresponds to a win rate of like 80%. But the average reward is 0.6 because losses are -1. So now what this is calculating here is a bunch of statistics on how the search policy right here. Now I'm passing into this function calculates this the average reward from this policy. The policy I'm using now is the search policy. Okay, so every state I'm conducting this search, and I'm evaluating it on different numbers of simulations. So this is with just 2 simulations, 20, 200, and 1,000. Okay, we can see the initial performance is this. If we run the search with only 2 simulations, we don't really expect much of an improvement. But what's nice to see verified is that it doesn't ruin the performance, right? It's only leading to something comparable and maybe a slight improvement. Then if we allocate more simulations, we can see as we go up here, up to like 200, now we have a pretty big improvement, right? And now if we do 1,000 simulations, which is like the scenario here, we've now taken a function that only had a 0.6 average performance and increased it to 0.77, close to 0.78. So this is like, now the downside of this is it's a much slower process, but we're starting from the premise that we have some budget to work with. So here, if we're looking like how long does this actually take to run? This is showing, sorry, here I'm just benchmarking down here. This is like the original policy function that we started with. So evaluating this one time, it only takes 5 microseconds. If I perform the search with only 2 simulations, it takes like 100 microseconds. So it's like 20 times slower. And then as we go here, I mean, still, if you have a budget of like a few seconds to work with for a move, even this, right, this is only 128 milliseconds. We're doing this with 1,000 simulations. So it's still, that's 24,000 times slower than our policy function. It turns out if a lot of this, it looks worse than it is because if you look at the profile of this running, a lot of this time is spent on the step function, which is part of the environment. This is like how the simulation works. Normally, when you do a lot of simulations, you're worried about the evaluation of the policy function, right? That should be the expensive thing. Because I have this greedy opponent that's being calculated, this MDP is a little bit slow in the step function. So this, in reality, you should, ideally, if the step function is trivial, the number of times slower this process is should just be roughly like the number of simulations. So if it's 2 simulations, it should be like 2 times slower because you're evaluating the policy function twice instead of just 1 time. There's other things, there's other data allocations and stuff. So practically it might end up being slower than that. But this looks so much slower because of the step function here, which, this could be sped up a lot. Okay, so far, we've shown how conducting this search, even with very limited numbers of simulations, we can take an existing policy function and we can consistently produce an improvement upon that, right? Although it does take some amount of time to run these simulations. Also, when we generate one of these episodes, which showed here, we also have this tree data that we have. And part of this data, I was actually using it here. This is also calculated as part of the data collection, is the improved policy. And the improved policy is calculated directly from this formula. We'll see it lower down, but it's using the logit values and also the action values. You can see there's a more verbose version of it in here. yeah, calculating the improved policy. But here, yeah, there's this little, this is what I said is we're really sampling from this, the logits plus the completed Q values. Here, this just is this added step that if we're at a node where there's no samples have been collected, then we just fill in the Q values with the value estimate. And this is still fine. This doesn't ruin the policy improvement either. So once we generate an episode, like we can see that just applying the search, forming a policy out of the search leads to an improvement. And it leads to an improvement because the search is effectively close to sampling from this improved policy. Now, the thing that happens with an algorithm like AlphaZero is that we do this and we have an existing policy and we conduct this search and we collect data from the search, including these Q values and the improved policy that we collect. This is really what's happening in this, not AlphaZero, but this algorithm. What's unique to this algorithm is the fact that we actually directly compute an improved policy that we actually can store as a vector like this, rather than just try to mimic it with a visit count or say that, well, our improved policies should mimic the actions that were visited during the tree search. Here we have this very principled improvement where the search itself is going to improve the policy, and at the end of the search, we can use the tree statistics to compute an improved policy. But there's something else we can do with all this, which is we can take all this information and we can think of it instead as just trying to improve the policy for a single run, which is being done here. I mean, we can always do this. Like, however good our policy is, if it's not perfect, if it comes time to use it and we have a budget to work with, we should always do this. Like, if the goal is to perform as well as possible, whatever we have, whatever we've trained, we might as well improve it as much as we can at the time of using it. I mean, if we have the time to spare. However, we can also think of this process of data generation, instead of using it in real time, we can do this ahead of time as a way to generate data and then use that data as a training set to actually train an improved policy rather than just improving it in real time. So we can do both. We can improve it. We can improve the policy itself ahead of time and actually embed that in the parameters. And then when we deploy it, we can also improve it in real time. And the next step of all this, I've shown how we can generate these episodes with MCTS search, and we can collect these statistics about the search tree. And the next step, which I think we'll cover in the next meeting, because it's like we're already kind of close to the end of time, and it's a whole other topic that builds upon this, is thinking about how to take all this information and build a system where we generate data from an existing policy, and then we simultaneously use that data to train and improve policy. And then periodically, we can then update the distribution that we're using to generate the data, right? So like right now here, I'm using this fixed thing, this fixed policy, which is on the left here, and all the data being generated is from this fixed policy. We can think about starting out with this policy, generating a bunch of data with it, having a data set that should produce an improved policy, and then we can do training steps. We can copy the parameters, train it for a certain amount of time, and then after that amount of time, we can sort of take a checkpoint of the policy, push the new policy into the search, and then use that new policy to collect data. And that will be the concept of how this training loop works, where we're not just using it in real time, but we're using it as an alternative to actually train and improve policy. I already showed a way you can train a policy and lead to policy improvement, right? Which is where I trained this original policy, right? Like the thing we're working with, the thing with the 0.6 value, is the thing that we train with an actor-critic algorithm. And it's possible that you could train a perfect policy function with an algorithm like this, with an actor-critic method. So one thing that's definitely true is whatever you've trained, if it's not perfect, you can use the tree search to improve it in real time. We can use the tree search as a training method as well. The question of whether that is more efficient than training something like this with just an actor-critic algorithm or an independent learning algorithm is another question, which we can't really answer until we do a lot of benchmarking and things like that. But, you know, that's something we'll try to cover or think about for a future meeting. But depending on what computational resources you have, this method of training may be better or worse than a more traditional, like policy gradient method. It certainly had a lot of success in a lot of these environments. And in the paper, they talk about all these success cases of using it trained from scratch, like Go and Atari games with different parameters. And they also show how even with a very low number of samples, the algorithm is successful. This is comparing it like heuristic, which is an older version, to this version. And if you run heuristic with only 2 simulations, you don't get any improvement. And it's not until you get, a number of simulations comparable with a number of actions that heuristic works properly. But this paper doesn't, it compares it to previous versions. It doesn't compare this to like doing like independent value learning without the search. The idea is that the search leads to a lot of improvement in the training process. It's an efficient way, but you can think of it as sort of like an n-step look ahead value method as well. So, right, you would have to do testing in an environment like this and compare it to non-search training methods. The nice thing about the search is you can use it in real time, but I don't think it's not really clear that in every scenario that it is a superior training method to something else. Because right, you have all these other steps of like doing data collection, and then you're training it with supervised learning on the collected data set. Right, it does look in that way very similar to something like DQN, where you have this like replay buffer, but in this case, the replay buffer is created from the tree search. But so those are all things we'll look at next time, where we'll get into the sort of the data collection and then how the data collection works in parallel with the training, and then what kind of results you get using that. But are there any questions about stuff I went over today? And if there were things you weren't sure about, the previous meeting was recorded, and all the other things that cover like actor-critic methods and independent learning methods are also in the 2 playlists that cover reinforcement learning and multi-agent reinforcement learning.